I'm Antonio Sala, and in this video we will analyze the damped, because there is some friction, vibration modes of the free response of this system. In this system, the input was the displacement of the rightmost end in here, but as we are going to analyze the free response, in fact input will be assumed to be 0 in all of this video. The normalized state space representation had this form. It was developed in a prior video, so we just need to input these A and B matrices into MATLAB, so let's do it. I'll give some values to the constant parameters, the friction and spring coefficients, and the mass. So this is A, and this is B. And we will choose as outputs for our simulations the 3 positions which corresponds to states with indexes in the vector 1, 3, and 5. So we'll put the first, third, and fifth states. In order to simulate this system, we will create a control system toolbox object named sys, or whatever name you wish to give it. And for instance, we can obtain the transfer function of the 3 displacements from the input, in this case of course transfer function matrix, because we have 3 outputs. But as we are studying the free response, then the input force response and transfer functions will not actually be relevant. So we are interested in the free response modes. What do we understand as modes? Modes will be associated to eigenvectors and eigenvalues of a matrix. We will quickly review the theory. It's not the goal of this video, the theory, but the MATLAB simulation and understanding of all this. You may pause and read this at your own pace, but if I can diagonalize a matrix like this, D must be diagonal, distinct eigenvalues. Then if I make this eigenvector change a variable, this is obviously equivalent. Doing some manipulations, we can see that the derivatives of these new variables xi end up being a diagonal matrix times xi, so dynamics is decoupled, and the system can be expressed as a collection of first-order dynamics. Each of the xi has this differential equation, being lambda I the diagonal element in the ith position in D, and of course the solution to this differential equation is the exponential. So lambda I are the poles of the system, and xi are the modes associated to that pole in these new coordinates, but in the old coordinates. If I set a single element of xi equal to 1 and the rest of 0, then, thinking in this expression, it ends up corresponding to an initial condition being the ith column of the eigenvector matrix V. So this is the theory. Let's go with a numerical computation. So we compute the eigenvalue decomposition. So columns of B are the eigenvectors, and the diagonal of D are the eigenvalues of matrix A. They come in complex conjugate pairs, which means that complex exponentials end up being oscillatory responses with sinus and cosinus. The real part gives rise to the decay rate, so we will have this exponential in the response times some cosinus and sinus of some omega t, and omega will be the imaginary part. 0.76, 1.41, 1.84. So this will be the shape of the response of each of the modes, and the free response will be a superposition of these 3 exponentials and oscillations. Settling time will be roughly 3 or 4, or pi, depending on the textbook, divided by the real part, 63 seconds. And the oscillation frequencies, these 1.8, 1.4, and 0.76, I will sort them in increasing order, as usual in mechanical engineering. So this eigenvalue, I will name it mode 1. This eigenvalue will be mode 2. And this eigenvalue will be mode 3 in increasing frequency order, as I said. Good. If I compute the oscillation period, 2 pi over the frequency gives 8, 4, and 3 seconds of oscillation period of the modes. So let us analyze and simulate each of these decoupled complex exponential responses in order to better understand its meaning in the spring system. If we start with mode 1, this is the eigenvalue. It was in position 5. Sixth one is the same but conjugate. And let's say the eigenvector, just the piece corresponding to the indexes, meaning positions, because it's the only thing we will see in the plots in a few seconds. Well, they have this luckily real and positive values. So in this free response mode, it seems that all positions move in phase. And if I scale, so dividing by the first component so that the first component is 1, we understand better what it means. It means that in this mode, left and right masses move with a given amplitude, and center mass moves with an amplitude of square root of 2 times larger amplitude, and they move in phase. I can do this polar plot stuff, or plotting this 1 square root of 2 1 stuff, indicating that the three masses are in phase. These are 1 and 3, 2 slightly larger amplitude. These are 1 and 3 and 2 slightly larger amplitude. Time response, if we set the initial condition to the real part of the associated eigenvector, the initial command running for a minute, which is roughly the settling time we determined earlier on, yields a simulation that, as expected, the three masses move in phase and the oscillations take roughly 1 minute to disappear or to be below 5% of the initial amplitude. And if we zoom, the period of the oscillations must be 8.2 seconds. And indeed, we can check that the period in the simulation coincides with what theory predicts. We have a nicer way of understanding this, because in another videos we discussed animation code. I am not explaining that animation code here. You can just watch the related video or just download or inspect the code. And here, if I set an initial condition in the direction of the eigenvector for mode 1, the fifth column of the matrix, well, if I simulate 80 seconds, these are the initial conditions, and here it is the simulation. Some oscillations with the three masses moving in phase that take roughly 60-something seconds to disappear. But okay, I will stop my simulation in 80. Here is it, settling time. And well, we finish here the simulation of mode 1, so with this animation we understand in a better way what this mode actually means. If we do the same with the second mode, with a slightly larger frequency, then eigenvector indexes related to position are these ones so well up, they are complex. How can we interpret that? Well, this complex means sort of that the picture was taken in the middle of an oscillation. So this is kind of informally, but okay, if I divide by the first element, so that dividing in complex domain is kind of dividing by the modulus and rotating, well, if I put the first one in phase and I move the same way the other ones, then this is 1, 0, minus 1 is the meaning of the second mode. In polar coordinates, it means that masses 1 and 3 move with the same amplitude but in opposed phase, and mass 2 remains without moving. Putting the third eigenvector real part as initial condition and simulating with initial command, indeed we see that the central mass is not moving, see this 10 to the minus 16, and the left and right masses move with 180 degrees of phase shift. If I now execute the animation with a new eigenvector, then here it is, the animation in which red and blue masses move with opposite phase and the green mass does not move. This is the second damped vibration mode that, as the first one, vanishes in around 63-65 seconds. Settling time now, only residual vibration remaining, and well, I finished simulation at 80 because I wished to. Again, the oscillation period, 4.4 seconds. If we zoom in the initial condition response, indeed, we can confirm that the oscillation period is as theory predicted. To end, we just need the third mode. This is the eigenvalue, largest frequency, 1.8 radians per second. Again, the position picture was taken in the middle of an oscillation, so if I scale and rotate, now we have 1 minus square root of 2 and 1 again. So the meaning is that in this mode, masses 1 and 3 move in phase, but the central mass moves in opposite phase, loading the corresponding eigenvector real part as initial condition. We indeed get that plot in which the top and bottom plots move in phase, the central plot moves in opposite phase, 180 degrees shift, and if we zoom in, oscillation period of 3.4 seconds is indeed achieved. And showing now the animation. Here we have the animation of said third vibration mode, in which the central mass moves in opposite phase to the other ones, and the frequency of the oscillations is higher than in the previous modes. Again, after 65 seconds, only a residual vibration remains compared to the initial one. Say 95% of the amplitude has vanished. We finish the video here just by concluding that the diagonalization of the A matrix identifies the free response modes. Real part can be used to compute settling time, imaginary part computes the oscillation frequency, and the eigenvector tells us the shape of this vibration mode, and of course, if initial conditions are not exactly one of the eigenvectors, then the overall response will be, by superposition, as in this case, will be a mixture of the responses associated to each of the modes. As I did not have, collision detection in the initial stages, masses overlapped, but okay, I guess that you get the message. Good. So this is it. We end up the video here. So thanks for watching.